Good morning. This guy is kind of fascinating, primarily because he really established the size of the Milky Way and the position of the sun in the Milky Way. Now, before we get to that part of the lecture, it revealed to me, at least in doing the research, how important another ratio is. Last week we spoke about, or I guess maybe 2 weeks ago, we spoke about the ratio of neutrons to protons in the atom. This week we're going to talk about the ratio of surface area to volume, and specifically for a sphere. And it turns out, as you'll see, that has an awful lot of implications in many, many different areas, both in physics and biology. So I thought that was kind of interesting, and we'll go through some of those implications. He was born in 1885, passed away in 72, and for a very long time, which I was unaware of, 31 years, he was the head of the Harvard College Observatory. It's kind of interesting. He used a specific type of variable star called RR Lyrae to estimate the size of the Milky Way galaxy, and we'll go through how he determined how far away those stars were by using the relationship between the variable period, the time it took for a star to go through its complete cycle of brightening and darkening, and how that related to its absolute magnitude, to its true luminosity. He also proposed a theory called liquid water belt, which is now known as the habitable zone, which is the zone around a star distance from the star at which water can be in its liquid form due to the proper temperature based on the heat that's generated by the star. So he was born in Nashville, Missouri, in 1885. It's kind of interesting. In 1907, he went to study journalism at the University of Missouri. And he was told that the School of Journalism wouldn't be opening for a year. So he decided to study the first subject he came across in the directory of the courses, and it was archaeology. He said, I can't pronounce that, so he went to the next one, found astronomy, and that's what he signed up for. It's strange, how these little coincidences and different things that happen at random have affected the course of science throughout history. In 1911, he established methods to measure the sizes of stars using eclipsing binaries. So we know that many stars are what we call binary stars. There's a smaller star that's in orbit around a larger one. In many cases, not in all cases, but in many cases, the star is the smaller star is going in front of the larger one along our line of sight. Okay, instead of going around like this, it's going around like this. So when the smaller star comes in front of the larger star, the light from the larger star is dimmed by a small amount. And so with sensitive instruments, we can establish what is known as a light curve, okay, which shows the dimming and brightening of the light that's coming from the larger star. So when the smaller star gets in front of the larger star, it dims the light a little bit. And many stars exhibit this characteristic. if we then measure how long it takes the smaller star to go in front of the larger star, and knowing the mass of the larger star from spectroscopy, in other words, we look at the basically the temperature of the larger star and relate that to its mass, okay? So we know the mass, we know the period of the orbit, and from those two things we can calculate the mass of the larger star. And by knowing the mass, we can get the size. So that's, getting this small amount of information. This is what astronomers are good at, right? From the little bit of information that comes to us in the light and other radiation from that star, we can determine an awful lot about the star. He also identified the Cepheid variable type stars as pulsating variables. So that's another way in which the light from a star varies. Just intrinsically, there's an imbalance between the gravitational forces that are constantly trying to collapse the star versus the expulsionary or outward forces that are due to the fusion that's going on inside the star. And if there's an imbalance to a certain extent, every star has some imbalance, but if it's a great enough imbalance, the star will constantly pulsate. So as it collapses, it will get brighter. And as it expands, it will get dimmer. And so it's in itself, it's an intrinsic variable. Okay, instead of something that's caused by the orbiting of a second star. So then he began to study these RR Lyrae stars, which are found only in certain clusters of stars within the Milky Way galaxy. The Milky Way is our galaxy. Okay, so these stars are relatively close by compared to more distant objects. So he, in 1914, began to study those stars. By the way, that was the year he got married. And 7 years later, he became the director of the Harvard College Observatory in 1921. He published his first book in 1929. There was a book written by a guy named Immanuel Velikovsky called Worlds in Collision. Now, Worlds in Collision is a very interesting book, and it's heavily referenced. I mean, he did a lot of research for it. Immanuel Velikovsky was a Russian expatriate psychiatrist. He was the son of a rabbi. I think he was the chief rabbi of Great Britain. But he was a scientist of sorts. And he wrote this book about a theory basically that said that the Exodus from Egypt, which is well documented in the Old Testament, was, and many of the events that surrounded it, and there were 10 plagues that were visited upon the Egyptians. Well, he found similar plagues in many different civilizations at that time, okay? He said it was due to the fact that Venus was initially thrown into orbit. Maybe it was an asteroid, maybe it was a comet, but it wasn't initially one of the planets in the solar system. And because it passed so close to the Earth, it caused these tremendous disruptions, volcanic eruptions, the river turning red with lava, blood, the raining down of various volcanic ejected particles, earthquakes, the hills skip like rams. Okay, so he had this kind of theory that Venus almost collided with the Earth. And a lot of scientists disagreed with that. And Shapley was one of the leading scientists that lectured against this particular theory. That was an interesting book to read, Worlds in Collision.
Oh, he's a psychiatrist.
Yeah, he was a psychiatrist. I think he was a chemist as well. That for some reason I thought he was a chemist. In 1953, he wrote the liquid water belt theory after a guy that came out who I never heard of, Hubertus Stronghold. If I had ever heard of him, I wouldn't remember that name. And he passed away in 1972 in Boulder, Colorado. Okay, well that was what I already talked about his University of Missouri choice of subjects. So there's various different ways that we determine the distance to stellar objects. And we're going to go through these in more detail, but just to give you an overview. If the object is close enough, like the moon, okay, we can actually aim radar or lasers at it. There's a reflector, in fact, that one of the Apollo missions placed on the moon. It's a mirror, and we know exactly where it is. We can aim a laser at it and measure the time it takes to get a reflection. So a pulsing laser, and then we measure the reflection. We can do the same thing with radar for many objects in the solar system. So that's one way. We measure the time it takes. We know the distance because we know the speed of light. Nearby stars, we can use the method of parallax, and we'll go through that in detail, whereby look at the difference between, or the angle between that particular object and a distant star. Wait 6 months, the Earth is now moved around to a different position, measure the angle again, and we use trigonometry to figure out the distance. For objects in the Milky Way, we can do something called main sequence fitting, whereby we can look at the spectrum of the light that's coming from that object. And the spectrum tells us what the temperature, basically, of that object is. If we know the temperature, then we basically know the absolute magnitude, really the intrinsic brightness of that object, okay? And then we look at it and we say, well, it's not that bright, okay? So it must be further than a certain distance away, and we can then calculate the distance. And we'll go through that in detail. For nearby galaxies, we can use the relationship between this period of variability with variable stars like the Cepheid variables and the absolute magnitude of the star. So again, we look at the absolute, the intrinsic brightness versus the actual brightness. We can figure out the distance. And finally, for clusters, we can look at the difference or the relationship between the variability called the Tully-Fisher relation, no relation to you, I don't think, David, and the distance or the brightness of that star. So there's all these different ways that we have of measuring distance. We also have the Hubble formula, which says the further away an object is, the faster it's moving away from us. So if we measure the Doppler shift, which we've talked about, we can determine how fast it's moving away from us. And from that, using Hubble's relationship, we can determine the distance. So those are all the different ways that we can look at the distance to an object, or determine the distance to an object. So radar ranging basically we have a pulsating radar. We send out a radio signal, and then we turn off the transmitter for a moment and wait for an echo at that frequency. And since we know that radio waves travel at the speed of light, all electromagnetic radiation travels at the speed of light, we can figure out how far away the target is, okay? It only works for targets that are relatively close, okay? Because if you send a radio wave out into space, first of all, the wave expands a little bit, which means the signal is weakened, okay? And it has to go through a lot of clouds of gas and dust. So eventually you get to the point where you don't hear the echo. So it only works for objects that are relatively close. Now, of course, the FAA uses this to track the 3,500 or so flights that are in the air at any given time over the United States. We have to talk now about the parameters of the sphere, because I want to eventually explain something called the inverse square law, which basically says that if you double the distance to an object or to a source of light or radiation of any kind, the signal will be reduced to 1/4. So it's 1/2 squared. Okay? If you triple the distance, it'll be 1/8, or 1/2 cubed, 2 to the third power. If you quadruple the distance, it's 1/16, 1/2 to the fourth power. So light, electromagnetic radiation, and very interestingly, gravity obey this inverse square law. And that's why scientists think that gravity is somehow related to electromagnetic radiation. Something called the unified field theory. Einstein was never able to prove it. We have recently, of course, detected what are called gravitational waves. So there's some indication that there's some relationship between gravity and electromagnetic radiation. You're saying no. You're saying that because you don't believe there's a relationship?
Well, I believe the relationship is inverse square, but it doesn't prove there's any electromagnetic.
Okay.
Just nothing travels faster than the speed of light. And it doesn't mean that gravity waves are electromagnetic.
Yeah.
Gravity is the bending of space-time.
It's a tenuous relation.
Tenuous conjecture.
Yes. I agree. But this led me, when I started looking at this, I said, okay, this will be easy to prove. The surface area of a sphere is related to the radius squared, okay? So the further you get from the center of the sphere, the larger the surface area, and it goes up as the square of the radius. So if you move twice as far from the center of the sphere, you have 4 times the surface area. If you move 3 times as far from the center, you have 8 times the surface area.
You keep taking powers, but it's the square.
I'm sorry, 9. Okay?
But it's interesting, it lucks out for the 2 and the 4.
Yeah, so the 4 times as far
It
as
doesn't go to
my,
the third power, goes to the square.
yeah,
Right.
so it's
You
9
want to get the third
times,
power,
right,
so it's 9.
right,
We're right.
okay. So we can figure out the surface area of a sphere, and one way you can do that using trigonometry is to divide up the surface area into plane figures, which are combinations of rectangles and triangles. And if you do that with smaller and smaller rectangles and triangles, you approach, you never quite reach, but you approach the surface area, which is how you can, one way you can derive the formula for the surface area of a sphere, which is 4 pi r squared. Okay? So I wrote a program. Had to do that, right? And what I did was, I said, okay, let's assume that we have circles, okay? We're going to use circles now. And these circles are going to expand as you move further away from the very top of the sphere toward the center, and then it'll shrink again as you move away. So here's a sideways look at what I did. I started with a very small circle, and I let it expand, and then I let it contract. And each time I measured the area of the circle, which we know is pi r squared, okay? And I summed them up. And I did this for about 100,000 times, and the last 9 lines of the program gave me a surface area for a sphere, I think with a radius of 1. And this is the actual calculation. I'm sorry, this is the volume. I was getting the volume, okay, of the sphere. And this is the calculation of 4/3 pi r cubed, which is the volume of the sphere. Dividing that by the actual number that I got, or dividing it into the actual number I got, gave you a value very close to 1. Wasn't perfect, but it was pretty good, okay? So we know the volume of the sphere is 4/3 pi r cubed, okay? And from that you can derive the surface area of the sphere is pi r squared. So here's the interesting thing. If you take the ratio of the surface area to the volume, okay, of different objects, you get these numbers. So for this object, which is a tetrahedron, is 7.21. For a cube, now a cube is what we call a regular solid, which means all of its sides are equal, right? A regular cube. The ratio is 6, okay? For an octahedron, the ratio drops to 5.72. For a dodecahedron, 12 sides, I guess. 12 sides? Yeah. It's 5.31. You notice a trend here. It's dropping, okay? A capsule is 5.25, roughly. An icosahedron, God knows how many sides that is, 5.148. A sphere, it's about 4.83. A sphere, and nothing is less than a sphere. A sphere has the lowest ratio of surface area to volume of any regular object. Okay? The lowest ratio. So that's an important fact to remember. In physical chemistry, materials that have a high surface area to volume ratio, okay, that is, they have a very small diameter and they're very porous or otherwise not compact, react at much faster rates than monolithic materials because more surface area is available to react, okay, compared to the volume, okay, compared to the volume. Examples include grain dust. Grain itself isn't typically flammable, but grain dust is explosive. Finely ground salt dissolves much more quickly than coarse salt. So a high surface area to volume ratio provides a strong driving force to speed up thermodynamic processes. Okay? Here's a picture of an old-fashioned radiator. Why is a radiator shaped the way it is? Well, if it was a sphere, okay, it would have a low surface area to volume ratio, which means it's harder for heat to escape. What you want is a very high ratio. You want a lot of surface area for a low volume so that the heat can get out more readily. So what did they do? They corrugated the surface to give it more surface area for the volume. Okay? So the heat can escape more readily. You don't want to trap the heat inside. In biology, the ratio between the surface area and the volume of cells and organisms has an enormous impact. Okay? For example, many aquatic microorganisms have an increased surface area to increase their drag in the water. This reduces their rate of sink and allows them to remain near the surface with less energy expenditure. An increased surface area to volume ratio also means increased exposure to the environment. So the finely branched appendages of filter feeders, such as krill, provide a large surface area to sift the water for food. Individual organs like the lung have numerous internal branchings that increase the surface area. In the case of the lung, the large surface supports gas exchange. Again, it's easier for the gas to exchange with other gases in the bloodstream. Okay? So it brings oxygen into the blood more easily and releases carbon dioxide from the blood more easily. Similarly, the small intestine has a finely wrinkled internal surface, allowing the body to absorb nutrients more efficiently. Cells can achieve a high surface area to volume ratio with an elaborately convoluted surface, like the radiator, okay? And like the microvilli lining the small intestine. An increased surface area, however, can also lead to biological problems. More contact with the environment through the surface of a cell or an organ relative to its volume increases the loss of water and dissolved substances. High surface area to volume ratios also present problems of temperature control in unfavorable environments. The surface to volume ratios of organisms of different sizes also leads to some biological rules, such as a rule called Bergmann's rule. And what Bergmann did was he looked in Sweden. Oh, and by the way, that's a map of Sweden on the graph. He looked at the average body mass of moose versus their latitude. And he noticed that at higher latitudes, colder temperatures, right, the body mass was greater. Okay? So if the body mass is greater, then the surface area to volume, okay, is less, right? It's got to be less. Because mass goes up as volume cubed. Volume goes up as mass cubed, whereas surface area goes up as mass squared, basically. Okay? So they retain the heat better. Okay? So the animals that were more massive could retain heat better and could survive at colder temperatures. Fire spread. In the context of wildfires, the ratio of the surface area of a solid fuel to its volume is an important measurement. Fire spread behavior is frequently correlated to the surface area to volume ratio of the fuel, so leaves and branches. The higher its value, a leaf is almost all surface area with little volume, the faster a particle responds to changes in environmental conditions. I mean, a leaf is flat, right? So the volume is almost nothing, but the surface area is very great. So temperature or moisture affects the leaf much more readily. Higher values are also correlated to shorter fuel ignition times, and so if there are a lot of leaves, a lot of brush, fires spread faster, more reactive to the environment. Planetary cooling. A body of icy or rocky material in outer space may, if it can build and retain sufficient heat, and alter its surface through volcanic or tectonic activity. The length of time through which a planetary body can maintain surface-altering activity depends on how well it retains heat, and this is governed by its surface area to volume ratio. Higher ratios do not retain heat well. More surface area for the volume. Yes?
When you were talking about the firefighters, the fires, can the firefighters try to do that to protect them the way they spread? Can they do something to change that? Like
What are you going to do to change? I mean, there's so many leaves. How are you going to change it?
Well, no, but I'm not talking about the leaves. I'm talking about something bigger than the leaves to stop it from getting all the houses and everything, so they can, you know, do something.
Main thing is
to
to not deny oxygen by spreading water and other chemicals. That's how you kill a fire.
Preventive type of situation.
So higher ratios of surface area
Yeah.
to volume do not retain heat well. The more surface area to volume you have, the faster heat can escape. Okay? For Vesta, which is an asteroid, the ratio is so high that astronomers were surprised to find it didn't have brief volcanic activity. So it's a very small object, okay? Small object means that the surface area to volume ratio is going to be higher. The Moon, Mercury, and Mars have radio in the low thousands of kilometers. They have retained heat well enough to have some very localized and infrequent volcanic activity. Venus and Earth, with more mass, okay, so the surface area to volume ratio is smaller, have sufficiently low surface area to volume ratios so that heat loss is minimal and volcanic activity is therefore more frequent. Interesting. Why are planets roughly spherical? Oh, and by the way, I didn't mention, but let me go back for a moment to the moose. I recently saw something on educational TV about mastodons. And this guy in Siberia who is digging up mastodon bones, extracting the DNA, sending it to a university in the States where they are trying to reconnect or reestablish a mastodon. And he said, we're going to, and the professor said, eventually, you know, we'll get a big box and we'll put a mastodon in it, send it off to Siberia. The mastodons, of course, were extremely massive, okay? So they had low surface area to volume and were able to retain heat in their bodies and survive at higher latitudes.
Good luck in climate change.
Yeah, good luck getting the DNA.
Climate change.
Yeah, with climate change. Yeah.
It gets hotter in Siberia.
Elephants are the same, And a lot of elephants live in rather hot climates. They're always in the water. They're splashing water on themselves constantly to cool off, because they're losing so much heat. Retaining so much heat due to their high ratio. Okay. Gravity pulls matter toward a local common barycenter. Okay? So what's that mean? For any object, no matter how it's shaped, there's a center of gravity. Okay? In physics, the center of gravity is basically the point at which you can consider all of the mass of the object to operate, to be concentrated. Okay? So every object, no matter how it's shaped, has some kind of a center of gravity. Okay? It's kind of the average of all the matter in the vicinity. When you have a lot of matter, of course, you have a lot of gravity. You have a strong gravitational attraction. When you get enough matter, the weight produced under the gravity will cause even rocks to crack and split. So at some point, gravitational attraction is stronger than the binding forces, the material strength of rock. Okay? If gravity gets strong enough to crack rocks, okay, the rocks crack and they begin to roll downhill, so to speak, toward the center of gravity. Okay? And as that happens, the shape of the object approaches a sphere. It's the most efficient shape, right? It's got the lowest ratio of surface area to volume. Okay? This starts to happen if the collection of matter is about more than 600 kilometers across, if it's rock, okay? And less if it's ice. Ice doesn't hold together as well as rock, okay? Eventually, all matter gets as close as it can be to the center of gravity. It's all rolled downhill, so to speak. There will be local variations, okay? The binding force of rock and ducks and trees and humans is still there. But on the whole, it's spherical. The Earth is roughly spherical. Not exactly, but roughly. If you scale down the Earth to the size of a basketball, the difference of the highest and lowest point on Earth would be much, much smaller than the bumps on a real basketball. It was pretty close to being a sphere. Everybody get this?
No.
Okay, understand what's happening?
That's what limits the height of buildings.
Pardon?
Limits the height of buildings. They collapse under their own weight.
Yeah. And that's why on the moon, for example, we could build a 10-story building out of balsa wood because gravity is so much weaker on the moon.
What impact does the spinning of the Earth have on?
Very little, but it can be calculated. But it's, at the equator, the centrifugal reaction is stronger than at the pole, but not that much.
Is it like 20-mile difference?
Yeah, it's not much. Yeah.
There's a bulge in the center of the Earth because of that spinning.
Yeah, it's actually a little bit south of the equator.
Yes.
Yeah, the bulge is a little bit south of the equator. That's because of the uneven distribution of mass on the Earth, I guess. Yeah. Deimos is the smaller and outermost of the two natural satellites of the planet Mars. It has a mean radius of about 3.5 miles. Okay, goes around Mars in 30 hours. It's really going very fast. It's obviously a captured pebble from the asteroid belt. It's not big enough to form a sphere. It doesn't have enough mass. It doesn't have enough gravity. So it's got this irregular shape. And the same is true of Phobos, which is the other moon, and also very small. Excuse me. For a fixed volume, a sphere is the shape with the lowest surface area to volume ratio. Surface tension is minimized when a drop forms a sphere. Why is there surface tension, and what is it? Well, at the surface of a liquid, there's more attractive force pulling the molecules down and together. So it forms like a skin on the surface, which enables small insects to walk on the surface of the water. It also forms a slight, what we call meniscus. As the water surface approaches the side of a glass, for example, it curves upward slightly because the glass is attracting the molecules more than the air on the other side. So they climb up the wall of the glass a little bit. So that means that if you have a drop of liquid, it's going to try to form a spherical shape. It won't succeed totally, especially if it's moving. One part of it will flatten out. But droplets are formed because of this attraction, okay, and this attempt to try to get into the most efficient shape of a sphere. A sphere exposes less surface area for the same amount of volume for a cube of ice. So if you have a cube that's the same volume as a sphere, the sphere will actually have a lot less surface area, okay, than compared to, a cube. The less surface area that's exposed to the warm liquid, the slower the ice will melt. So bartenders use spherical ice cubes. They don't dilute the liquid as fast, and they don't melt as fast as cubical ice cubes. And next time you go to a bar, tell the bartender, make sure I get spherical ice cubes. And you can explain to him why, if he's interested, and if you're able.
Yes, about the how much people listen, yeah.
So we look at animals, okay? A bird, for example, has a linear measure of about 1/2 foot, let's say, 6 inches, and a surface area proportional to that of 0.25. 0.5 times 0.5 is 0.25. The volume in cubic feet is proportional to the linear measurement cubed. So 0.5 cubed is 0.5 times 0.5 times 0.5 is 0.125. So the ratio of surface area to volume for a bird is about 2. Okay? So if we divide, in other words, 0.25 by 0.125, we get 2. Small animals, birds included, must eat constantly because the stomach volume is much smaller compared to the surface area. They have a high metabolic rate. They lose heat rapidly, okay? Because the surface area to volume ratio is higher. For a human, the ratio is about 0.74. For an elephant, with about a 6-foot linear measure, let's say, maybe that's too small, actually, but let's say it's 6. The surface area proportional to that squared is 36. The volume, however, is proportional to 6 cubed, which is 216. The ratio, therefore, is very low, 0.167. So the elephant retains heat very well, does not respond to changes in the environment very well, and has to constantly think of cooling and thrives better in colder climates. Fascinating, huh? Yeah.
Elephants should go to the North Pole, right?
Pardon?
All the elephants should move towards the North Pole.
It should be, it should be.
The ratio is just the reciprocal of the size, so it should be 0.67 for the human.
Do I have a mistake?
Yeah. Just the reciprocal of 1.5.
The 0.74 is wrong? What is it?
It should be 0.67, just to be consistent.
So you're arguing about seven
It's the
hundredths.
reciprocal of the
He's arguing about 700ths. I just want to point that out.
Yes.
Thank you for your correction.
point out the consistency of the arithmetic here.
Yeah, yeah, okay.
About 2/3.
So what's the comments about?
Yeah, it's about 2/3, okay, yeah. All right. So let's talk about the inverse square law. Okay? I got so interested in this ratio business, I'm starting to write, I don't know what it'll become, maybe an article, maybe a book on ratios of different things, because it harkens back to the ratio of neutrons to protons. And by the way, the book I'm reading, which you loaned me, on the development of the atomic bomb, says that this ratio of surface area to volume for uranium is such that they figured out how much uranium they would need to capture the neutrons in the uranium to have a chain reaction. And they started out with a huge amount, but eventually it came down to about 2 pounds of uranium. If you can get 2 pounds of uranium together, then you can have a chain
235,
reaction.
Right? U-235.
Yeah, 235, right, right.
Which book is that? What's the name of it?
The development, what's the title? Development of the atomic bomb.
Making of the Atomic Bomb, Robert Rhodes?
Robert Rhodes, yeah,
Oh, Rhodes, okay.
yeah. Fascinating book. Just one paragraph is found in it. It said that, and it struck a chord. So I'm so interested in ratios that I'm writing something about ratios in the universe. There are many different ratios, and by the way, as you can see, they have implications in many different areas. Biology, chemistry, physics.
What's the famous Leonardo da Vinci ratio? He had a ratio.
The golden ratio for a
the
playing
things,
figure,
the arm, the body.
Yeah,
you
yeah.
know, and he says leaves actually have it. You know, it's all based on ratios.
yeah, yeah. Yes, sir.
Just going to point out, you mentioned the other book, Hitler's Gift.
Yes.
Peierls was the German scientist who worked out that ratio, and was one of the scientists that left Germany because of Hitler. He went to live in England.
What was his name?
Peierls, P-E-I...
Rudolf Peierls.
Yeah, Rudolf Peierls.
He was a friend of Beta's.
Oh, really? Okay. Yeah, and Niels Bohr, by the way, Niels Bohr,
Estimating this number, they previously had got a lot of faulty theories about how what the critical mass would be.
oh, okay,
About the
Yeah.
correct ways.
yeah.
And told the Allies that yes, a bomb is possible,
Mhm.
when the general feeling back in Germany was that it would take too much uranium to be practical.
Huh. So they made a mistake in their calculations.
They made a mistake in injecting their best scientists.
Yeah, right.
Thank goodness.
And I found another interesting thing I found in that book. Niels Bohr actually had an association formed, an organization that helped scientists get out of Germany. Yeah. So he was helping that flow of brain talent to leave Germany. Okay, so let's talk about the inverse square law now. So we know that the surface area of a sphere is proportional to the distance squared from the center, right? 4 pi r squared. So if we start with a light source at S, right here, and these red lines represent emissions of light, light beams, light rays, photons, whatever you want to call it, the surface area And visualize now a sphere around that source, okay? A sphere at a distance of r will have this surface area, okay? And that, let's say that's a unit of 1. Can be 1 square foot, whatever, okay? If you move to 2r, double the distance, you have 4 times the surface area. Clear? Okay. Now, if you have 4 times the surface area, but the same amount of radiation, that means the intensity of the radiation will be 1/4, right? It's got to be reduced, because now the same amount of radiation is going through a much larger area. Okay? If you go to 3r, then you have 9 times the area. Okay? So there are 9 of these squares, and the intensity, therefore, is 1/9. Well, we are right now about 4,000 miles from the center of the Earth. So if you went up 4,000 miles, the gravity, the gravitational attraction of the Earth on your body, okay, would be about 1/4 of what it is now. So if you weigh 125 pounds, you would weigh about 60 pounds at 4,000 miles up. If you went up another 4,000 miles, your weight would be reduced to 1/8, 1/9. How do I keep doing that?
It's R cubed, it doesn't go as R cubed.
Yeah,
It goes as R squared.
okay. 1/9. Okay? So you would weigh, what, about 15 pounds, something like that. And of course, if you went another 4,000 miles, then you would weigh 1/16, right? 1/16? Okay, check my math. Okay? Which means you'd be less than, probably about 8 pounds or something like that. And you've all seen pictures of them floating around in the capsules in the International Space Station. Okay. So electromagnetic radiation and gravity both obey an inverse square law. So if this is the brightness of the star, okay, it is going to fade, it's going to get dimmer according to this inverse square law.
Can I challenge that a second? The amount of light will hit a particular point, will dim by the inverse square law.
Right.
The star itself never gets dimmer, and if you were able to magnify it so it filled the frame, it would be absolutely as bright as if you were standing next to it. I mean, put it a different way. Let's take the moon.
Okay.
You've got a full moon.
Okay.
What exposure would you use on your camera? You would use the same exposure. The inverse square law has nothing to do with it. You would use the same exposure you do in bright daylight, because the moon's lit by bright daylight.
Oh, okay. Okay.
It's
Yeah. Yeah. But we can use this law in this way. When we look at the star, it has a certain brightness, okay? When we analyze the spectrum of the star, looking, breaking the light up into its various components, we can tell what the temperature of the star is, okay? And assuming the star follows a certain law of temperature versus brightness, okay, we can then say that the star has an intrinsic, inherent brightness of a certain amount. Now, obviously, it will not appear that bright to us with the naked eye, okay? So there's a difference in the brightness of the star. We can measure that brightness using instruments, okay? So we can quantify the brightness of the star. And so we can quantify the difference in brightness, and therefore we can say how far away we would have to move that star from a certain distance to be as bright as we observe it to be. Okay? And so we know how far away the star must be based on the difference between what we observe to be its brightness and what we know to be its intrinsic brightness. Does that make sense?
If you just say the intrinsic brightness is how bright it would be if we were 10 parsecs, which is just a defined distance
Right.
that they chose.
Right.
If you put all the stars at 10 parsecs and log down how bright they are, and then compare that with how bright you observe them to be,
Yeah.
you adjust the 10 parsecs accordingly.
And we're going to talk about a parsec in a moment, but it's a certain distance, about 3 light years, 3.26 light years. But so if you want to look at it that way, you can say, how bright would that star be? We're looking at it, it's not very bright. How bright would it be if it was 3.26 light years away? And if it got brighter, it means it's further away than 3.26 light years.
Factor 32. 10 parsecs.
32.6 light years, right. Okay. So that's just another picture. So it works with a light bulb. You know, if you took a light bulb, and as you move away from the light bulb, it gets dimmer, right? As you observe it. Okay? In the same way. Okay, so here's a parsec. A parsec is not a unit of time, okay? Despite the implication of its name. It is basically a unit of distance, okay? It means that if you look at this object from different points, okay, and the 2 different points here are the Earth and the Sun, okay? We know the Earth is 1 astronomical unit from the Sun. An astronomical unit is about 93 million miles, or about 8 1/3 light seconds. If you look at this object from these 2 positions, and the angle that's formed between the 2 light rays, basically, that are coming to your eye, is 1 minute of arc. Now, what's a minute of arc? It's 1/60th of a degree, right? That's 1 second, I'm sorry. 1 second of arc. So it's 1/3600th of a degree. A very small angle. Very small angle. Okay? Yeah, a minute of arc would be 1/60th. A second of arc is 1/3600th. A 60th of a 60th. Okay? So it's a very small angle. So parallax, using parallax only works for objects that are relatively close. If the object gets too far away, the angle gets too small and we can't measure it. Okay?
Wait, how do you actually measure it? You measure by comparing that star against its background?
Background, right.
And then if you've got a telescope with setting circles on it, you just turn those setting circles so that they line up the same way on each side, so it's that difference in
But
angle
it has to
on
be
the setting circles.
very finely
Right.
machined.
So,
Yeah.
So you've got setting circles on your telescope.
Yeah, but I can't do this.
But you can't measure it.
Not that finely,
Measure
no.
it off the plate.
Yeah.
You don't use the telescope.
Well, how do you measure it off the plate?
Using a ruler.
A ruler?
Yeah. You expand it large enough that you can take easy measurements of it.
Yeah, yeah.
That gives you a length of 8 inches. So where do you get the second half of that?
You know what that represents in terms of angle because of the scaling of the plate. And I point out that's 206,000. That's using the European decimal point.
No.
Thank you. See me after class.
Maybe change the periods and commas.
So parsecs are used for shorter distances only, okay? Because if it gets too far away, this angle gets so small that it can't be measured, even with our best instruments. So we use, for more distant objects, we can sometimes say they are kiloparsecs or megaparsecs or gigaparsecs at a distance. But we can't necessarily measure that directly. We have to use other methods to measure it. Then we convert into parsec or gigaparsecs or megaparsecs to just say that's the distance, okay? But the angle would be so small that we couldn't measure it directly.
Do they really use the sun, or they use the earth on the other side of the sun?
Yeah, instead of using the sun, they're actually waiting for the earth to come around to the other side of the sun so they can get a bigger angle. Okay, so if they get 2 AUs here, they can get a much better measurement at a greater distance. So they're measuring the position of the star relative to the distant, or what are called fixed stars. Okay, because if a star is far enough away, even though it may be moving at right angles to our line of sight, it doesn't show up as movement over a relatively long period of time, okay? So you can see that if the Earth is here, this might be the position of the star relative to these other fixed distant stars. When the Earth gets around to here, this star apparently has moved due to parallax, right? And, showed you that, right? So it's a different view. And so they can measure this angle, called the parallax angle, and determine, since we know this distance, this side of the triangle, if you know this side of the triangle, and you know this angle, then you can use the tangent of the angle, okay, to find the distance to the star by dividing the orbital radius by the tangent of that angle. The orbital radius is here, 1 astronomical unit, and you know this angle. So you can measure this side, which is the distance to the star. Straight trigonometry, okay? Tangent tables are available in any trigonometric text or on the internet, okay? Everybody understand that? If you know an angle and the side of a triangle, you can find the dimensions and other angles of the triangle, of a right triangle.
How do you get the angle off the photographic plate? Because you can measure the distance there between those 2 photographic plates when they're on either side.
How do you get this angle?
You're measuring a distance in inches between.
Yeah, it's very small, but you overlay the 2 plates, right? You just overlay the 2 plates.
So where do you get the angle from?
You get that distance, right?
Yeah.
Don't you know the angles to the 2 fixed stars?
Yeah.
So you can interpolate.
Yeah.
You know the angle to the star on the left and the star on the right.
Yeah, you know the angles. You know this
You know
angle
the position,
for this star and for this star, right?
You get that from the plate?
Right, no, you get that from this.
When you
Ephemeris.
do the measurements on the scope, you measure you aim the scope at a particular point, the same point. Then how far off that point is an angle of your target star?
Yeah.
And you read that from the scope.
So you might aim your, like if you aim your telescope at let's say this star, okay? So you could then measure the angle to this star.
Well, how do you measure the angle? That's what I'm asking.
I think the angles are so small that distances are the same as angles, basically.
You do it from plates
Distances
now.
are the same as angles.
The angles are so small. What happens is, when an angle gets very small, the change in the functions of the trig functions of the angle are basically the changes in the angle.
That's what I'm saying.
Yeah.
I had to dig out my refrigerator, I couldn't open the bins. Couldn't open the bins for the vegetable bins. So I had to angle, push the refrigerator over against the other side, away from where it was, and then angle it.
You see how useful astronomy is?
But I did it without it this time. I did it with no brains.
I believe it.
So if the star is too far away to use parallax,
Worked.
we can use what is called main sequence fitting, okay? So if we plot the surface temperature of the star against a luminosity, okay, we find that most stars lie in what is called the main sequence. Amazingly, almost straight line, okay, if we plot it on a graph. There are stars that are called white dwarfs that are toward the hot end of the surface temperature, but low in luminosity. And there are stars that are toward the cool end, but are much brighter than stars on the main sequence for the same temperature, okay? However, if we look at most stars, they fall on the main sequence. We can figure out what the absolute magnitude of those stars is, okay? If we get the absolute magnitude and we look at the star and get the apparent magnitude, then the distance can be found using this formula, okay? Where lowercase m is the apparent magnitude, uppercase M is the absolute magnitude. Very straightforward. We can identify stars on the main sequence or off the main sequence by virtue of their spectrum, because the chemical compositions of stars that have moved off of the main sequence is different from stars that are on the main sequence. Okay? So by looking at the spectrum of these stars, we can determine whether they're on the main sequence or not. Very straightforward. So if we have something called the standard candle, that simply means that we have a standard luminosity or brightness for a star of a given temperature and type, a chemical type, okay? So we compare the object's brightness against a known or measured brightness from objects that belong to the same class, okay? So if you spot a certain object like a star or supernova and determine that it is a standard candle, you can get its distance by measuring its brightness and comparing it to the known brightness of objects similar to it. So RR Lyrae stars are periodic variable stars. And where they are on the Hertzsprung-Russell diagram that I showed you is that they are a little bit to the left and below the main sequence, which falls in here. Okay? There seems to be what is called an instability strip on the Hertzsprung-Russell diagram. When stars get into this region, which is a certain spectral class and a certain brightness, inherent brightness, or absolute magnitude, as we say, they tend to become somewhat unstable, okay? Which means the forces of gravity and the forces of radiation, gravity trying to compress the star, radiation trying to expand it, become unstable. So the star begins to vary. It begins to oscillate. Okay? And as it begins to oscillate, it tends to have a certain period of oscillation, a certain time over which it goes through a complete cycle from dimness to brightness. Okay? RR Lyraes are spectral class A through F. And I told you my mnemonic for remembering these. Oh, be a fine girl, kiss me. And this should be an R. This should be an N, but those are the main spectral classes of stars and are related to brightness of stars on the main sequence. So the period of pulsation and the absolute magnitude of RR Lyraes make them good standard candles for relatively nearby targets, especially within the Milky Way. The Milky Way being our own galaxy. Beyond the Milky Way, since RR Lyrae are not as luminous as stars on the main sequence for their class, for their temperature, it becomes difficult to detect them. But for clusters within the Milky Way, we can see them pretty well. Sir?
You've got two strips up there, the Cepheid, the classic Cephids and the West Virginia variables.
Yeah.
Are those two different classes of stars, or is that an academic dispute?
They're slightly, well, when you say classes, they're different. They're slightly different spectral classes. Okay? So the Virginis are more in the G to K region, and the Cepheids are more in the F to G region. The Lyraes are in the A to F region, which means they're hotter, but they're not as luminous. Okay?
Three different
Yeah.
classes.
This is a better way to see it. There's two different classes of Cepheids, okay? And here are the Lyrae stars down here. So Lyrae stars, almost all of them have the same absolute magnitude. They don't change very much. These curves are much sharper, okay, and show much greater change as the temperature changes. But Lyraes, even though there's some temperature change, they don't change very much in brightness. Okay, and then we come to Tully Fisher. So you've seen now different ways of measuring distance to the stars. We started with radar, radio waves, okay? Then we looked at parallax. Then we looked at a couple of different ways of determining the absolute magnitude and comparing it to the apparent magnitude. Here's another way. It turns out that as a star rotates on its axis, like the sun rotates, the part of the sun that is moving away from us, okay, will show a shift in the spectral line, okay, toward the red end of the visible spectrum. It's called a red shift, okay? I tried to explain this to my wife, and she said, when can we go to the mall?
She couldn't care less.
The other side of the sun is going to show us a shift because it's approaching us toward the blue end of the spectrum. And you'll notice, by the way, that the sun, because it's a gas primarily, is rotating at different rates depending on the latitude away from the equator. Okay? So it's slightly slower at the pole than it is at the equator. What this does to the spectral line is it broadens it. Because if we look at all the light coming from the sun, some of it will be shifted toward the red, some toward the blue, and some will be right in the middle. So it broadens the spectral line. Okay? The combination of shifts in the spectral lines result in a widening of the line. So here you can see an object moving toward the observer, the wavelengths get shifted toward the blue end, moving away it gets shifted toward the red end. The number of stars in the Milky Way is estimated to be about 200 to 400 billion. You can only see about 5,000, 8,000 of these stars with the naked eye, and only about 2,500 of them at any one time from any spot on the Earth. The Milky Way is about 100,000 to 120,000 light years across. Its thickness, up and down, is about 1,000 light years, but there's a bulge in the center of about 12,000 light years. The position of the sun in the galaxy, which was determined by Shapley using the RR Lyrae stars, is about 27,000 light years from the center. And the orbit of the sun around the center of the galaxy takes about 230 million Earth years. And by the way, I should point out, and this will be a subject for a future lecture, when we look at the rates of rotation of different stars at different distances from the center of the galaxy, we would expect that to change based on the mass of the center of the galaxy. It doesn't. There's more matter there than meets the eye, literally. And that's where the idea of dark matter came from. So we don't see the change in orbital speed that we would expect, or for example, that we see of the planets, the further out planets moving around the sun more slowly. It doesn't happen with the galaxy. So the sun is in a rather innocuous neighborhood. It's a mediocre star, by the way. It's a G-type star. If we go back to the Hertzsprung-Russell diagram for a moment, the sun is right there. It's right in the middle. So it's not at any extreme on the Hertzsprung-Russell diagram. It's an average star in an average neighborhood in the galaxy, and the galaxy is a rather mediocre galaxy, not anything special about it. So for those of you who thought you would expand your egos by coming to this class and getting all this knowledge, just think about that.
It's going to evolve into a giant.
I'm sorry?
It's going to evolve into a giant.
Yes, it will eventually move up. It will become larger and hotter, and it will move into this area of the Hertzsprung-Russell diagram. But it's probably not going to get much hotter. It's just going to get bigger. And the reason it gets bigger is that the mass of the core is being used up. So the gravitational pull is being weakened, but it's still producing a lot of radiation. So it will begin to expand. Okay? And as it expands, well, the Earth will melt. In plain terms, the Earth will melt. Mars will probably melt.
Mars.
Probably about 5 billion years from now.
So it's doing it very slowly.
So in summary, objects in the solar system can be found, distances to those objects can be found using radar. measuring the time to receive an echo. Stars in our galaxy by parallax, measuring the angle. Stars in the Milky Way with main sequence fitting that are too far away for parallax, we can use the absolute versus apparent magnitude. Nearby galaxies, using variable stars, the period luminosity relationship. And galactic clusters of galaxies at great distances. If we look at supernovae, we know what their absolute magnitudes are, so we can use that same relationship to measure their distances.
So how do you measure apparent magnitude with your telescope? Is there does any astronomer?
Using instruments like photoelectric cells.
Oh,
Yeah,
okay.
yeah,
Makes
photoelectric
sense.
cells. Yeah, they have to have a standardized cell. Yeah, yeah. The ratio of surface area to volume has numerous and significant implications for the characteristics of many physical, biological, and environmental systems. Surface area of a sphere increases the square of the radius. So if you have a greater area for emissions from the center of the sphere, okay, then you lose heat more rapidly if the ratio is high. The smallest ratio is for a sphere. The emission of electromagnetic radiation and gravitational waves follow an inverse square law. Shapley used RR Lyrae variable stars to find the relationship between the period of pulsation and the absolute magnitude. Once he had the absolute magnitude, then he could figure out the distance. So he was able to determine the size of the galaxy. That was his major contribution. And the sun, which is a medium-sized star, occupies an unremarkable position in an ordinary galaxy 27,000 light years from the galactic center in a 230 million year orbit. Questions?
We have
Yes, sir.
time to figure out how to do something if you want to at this point.
I'm
I
sorry?
mean, do we have any time? We have a lot of time now to figure out things before it starts moving. Well,
Yeah, 5 billion years or so.
you know, if we start to use our brain.
Yeah.
Just go to another planet.
Pardon?
Go to another solar system.
We have to find another solar system.
Just
Right.
because it's been
For a time, it's interesting, for a time, some of the moons of Jupiter and Saturn will become warm enough to be habitable. For a time.
Oh,
Okay.
long enough to get on if you want to.
Yeah, yeah. And that may be what happens.
It's probably gonna.
We'll never know,
gonna
but
happen. I
that
mean,
may be what happens.
Who knows?
Yeah.
Start to use our real brain.
One of the charts was a corrugated view of the galaxy. One of the chart names had the word corrugated on it. Was that the same type of word used when you were talking about the radiator?
Yeah. Yeah,
Now,
it's the variation.
Straight up and down,
Yeah.
sideways.
What you are telling me, Anas, that if we survive more than 5 billion years, then we will have some problem.
Yeah, I don't give the probability of surviving more than 5 billion, much less 5 million, much less maybe 5 years.
You should
At the
have
rate
some-
we're going.
Not-
But yeah, if we survive that long, yeah, we'll have to find another solar system somewhere. Or maybe some of the outer objects for a time will be habitable, meaning that water can exist in a liquid form because the heat will be produced from a star that is much closer, in effect. The surface of the star will be much closer. We think there may, in fact, we're on Titan, we think that below the ice on Titan, there may be a liquid ocean. And in that ocean, there may be life. So what they're going to do is eventually drill through the ice, send sensors down, maybe with a camera, and see if they can get a picture of a shark or something. Also try to detect microorganisms. Yeah.
So,
Yeah, when you're talking about the Earth expanding eventually, enveloping.
The Earth, no, the sun.
The sun, yeah, the sun enveloping the Earth someday. Is that because, is the sun leaking gas out into space?
Yeah, it's burning fuel. So the mass is being reduced, which reduces the gravitational attraction.
Yeah, but I mean, the helium is produced from the hydrogen fusion.
It starts
So
burning.
is it being leaked
Oh,
out
yeah.
into space?
No.
But it's being burned. The mass is being reduced.
But I thought it started burning helium and then carbon it goes up to nuclear.
It goes
chain.
up a little bit,
Okay.
yeah.
But I thought because of that, it burns at a higher temperature
Right.
at the core. So because there's a higher temperature at the core, the gas has to expand. I guess what he's saying is the red giant, the surface temperature doesn't become any hotter because it's so much huger. I mean, when it moves out to the radius of the Earth, it's a tremendous radius for the sun. But the core temperature is much hotter because it's a higher nuclear fuel base. It's burning carbon and on a chain.
At the same time, it's burning mass, right? It's using up mass.
Burning mass,
Yeah, okay, I see.
So gravity is reduced, but the temperature goes up, so the pressure is greater, okay? So it expands.
And there's a solar wind, so it actually
Yeah,
is.
the boat's gonna start blasting off.
she has a question.
I suppose most of
Where,
it.
where is it? Do we have any idea?
Excuse me.
I can't hear you.
Do we have any idea of the source of the Earth's internal heat?
Do you have any idea of the
Oh,
source?
radioactivity in the core of the Earth.
And the collapse.
Yeah.
And the collapse, the original collapse.
And, yeah, an original collapse of the material, compression. Yeah, but there is a good deal of radioactivity too, yeah.
Is Venus closer to us than Mars? I mean, to the Earth?
Oh,
It's
about the
closer.
same, I think the distance is about the same.
Well, then why wouldn't we put some interest in Venus rather than
Oh,
Mars?
Venus has an atmosphere of almost pure carbon dioxide. The surface temperature on Venus is about 800 degrees.
This is the last one.
We couldn't even approach it, you know.
But you're
If
saying
we send a rocket to Venus, it would melt.
it would melt.
Yeah, we did.
Because we
Mars is the
Mars
closest,
It's more accessible,
other than the moon, yeah,
other than where?
the moon.
Oh, well.
We have equator on Earth.
I'm sorry?
We have equator on Earth,
Yeah.
on our Earth. But do other planets also have equator?
Oh, yeah. All the planets rotate.
They also have equator?
Yeah. Uh-huh.
What's special about the equator?
That's 92.
Yeah.
I saw a documentary on TV about the moon, and about where water is on the moon,
Yeah.
and the permanently shadowed craters that are permanently in the dark. That's where they plan to find water when they go back to the moon.
Yes. And if they find water, because chemically you can break water down into hydrogen and oxygen, they can make fuel. And if they can make fuel, they can use the moon as a launching pad to go to other objects.
In fact, they estimated there's something like 1 billion gallons of water in all the craters that are in the shadow.
Yeah. Which isn't a whole lot, yeah. Yeah. I think that there may eventually be a small colony on the moon, but I think for a long-term colony, it's going to be Mars. That's my own opinion. Thank you very much. Have a great week. I'll see you next week.